Hi there. This video is on Unit 3. It's about three things. First one is gas laws. You can see on the screen how real and ideal gases change, how real gases are different from ideal gases. Number 2 is about intermolecular forces, like how they dissolve, chromatography, and distillation. And then the third thing is about how physical properties might change based on their IMFs. So let's start with this one. I can analyze data to determine if a gas is deviated from ideal behavior. And that's what I have this chart up here for. So these, if you assume that they're all real gases, let's say it differently. If you assume they're all ideal gases and they're all the same number of moles, you could look at this and you can see the pressure is all the same. It really determines, the pressure is determined by the number of moles of the substance. And since we assume all gases to be the same, if you have 3 moles of the gas and all situations are the same, then it'll provide the same pressure. But we can see down here that SO2 has a different pressure. It's slightly lower. And so the question would be, which gas deviates from ideal gas law behavior? SO2 definitely does. And then why? That's the second part. I can explain how real gases behave, which causes the deviation from ideal gases. Okay, if we look at SO2 and draw its Lewis dot structure, it's actually kind of a weird one. It can be hard to draw, but it looks like this. And so by looking at the Lewis dot structure, one, you can see that it's a pretty massive molecule. Down here they have the molar mass of, that's the mass of the sample in grams. The molar mass is actually pretty big for gas-wise. And then the second thing, I can see that it's a polar molecule. I know that it's polar because if I look at the central atom, it has lone pairs, and automatically that's a polar molecule. It'll have this bent shape, and the lone pairs are on the top, and this lone pair bubble is where the electrons live, and that's really negative on that side compared to the positive part on this side. So I know it's a polar molecule. So just because it's a polar molecule really shows how things could deviate from ideal gas behavior. So down here are the 2 ways that you can deviate from ideal gas behavior. Let's hit this one on the right first because it has to do with the idea that it's polar. Real ideal gases will hit the sides and bounce around, and that provides the pressure. But your real gases will have an attraction to the other gases that are inside. You can see in this ideal gas picture, there's no attractions going on. But on the right side, you can see that there are attractions because they're real gases. Because of that, that gas molecule is attracted to the ones behind it. So it's like being pulled toward those. Because of that, it doesn't hit the side with as much force. And that's if you can take a look at the size of the arrows. The arrow here is very small, a red arrow, compared to the large arrow on the ideal gases. The arrow on the real gas is being smaller because it's being held back by the gases around it because it's polar and attracted to them. So the more polar or the higher IMFs that you happen to have, the less ideal behavior you will have. The other thing is no matter what gas you've got, if you're going to create a smaller volume, it's less likely it's going to behave as an ideal gas. But it'll be even more so if you happen to have a massive molecule. So either high in mass is indicative that it's going to be a large molecule because it has a large electron cloud that makes it a large, massive molecule. Or if you happen to have a lot of atoms all stuck together, it's just a lot of atoms molecule in general. The bigger the molecule, you can look at molar mass, the more likely it will deviate from ideal gas behavior. And that's because if you look here, as you shrink our volume, in other words, create high pressure, the volume of the actual gas molecules is actually taking up quite a bit of space in there. Since it's taking up quite a bit of space, it's creating, because it's taking up more space, and we assume that ideal gases do not take up any space, it will not follow our ideal gas behavior. That's a simpler way to say it. So the more mass in the molecule, the more likely it's going to deviate from ideal gas behavior as well. Okay, moving on to the next topic. And that would be this topic. The first one is about dissolving. These are about the different kinds of processes. And I think that from our first analysis, these problems were difficult for you because it's been a while that you've looked at it. You have to be able to draw how things dissolve. This was a problem that we just did on Friday. And what it asked you to do is actually show the dotted lines about how the hydrogen bonds happen. So this is water. These like Mickey Mouse ones are water. And then you can see that this is urea in here. And the hydrogens are these dark ones. So what's happening is there's a hydrogen bond between this oxygen's lone pairs and this hydrogen, which is very electron deficient. Another one you could draw is right here. Right here. Now this nitrogen, which is right here, it happens to have lone pairs parts, so you could have it attract, or right here, this is oxygen, a hydrogen bond right there too. So if you're going to draw dissolving, lots of times what you'll see is just like a calcium ion or ions, and you have to draw how water will go with that. There where you're going to want the oxygen, which is negative, or partially negative, I should say, being directed or pointing toward the positive part. You just want your positive and your negative being directed toward each other. So oxygen is partial negative, hydrogen is partial positive. Depending on what ion you have, you want to change your water molecule around. Now on the AP test, they're not going to have you draw anything because that's just, you have to be able to type everything and you can't type a drawing. So what you'll have to do is interpret something. So if you look at this picture over here, you might have to interpret it and say, how does this one dissolve? That's when you say the partial positive side of water, the hydrogen, is attracted to the partial negative side of the urea, which could be found on the nitrogen's lone pairs. But you want to use that word partial in order to do it, because you can't say the negative part of oxygen, the negative part of water, the oxygen side. It doesn't work like that, because that would suggest that water is an ionic compound and he doesn't have a negative and a positive. He has a partial negative and partial positive side, but not like a positive and a negative side. So I'd use the word partial there if you had to talk about it. The other part of this part is chromatography as well as distillation. I think that's why you guys ranked yourself pretty low, because you don't remember what those two parts are. That's okay. If we're looking at chromatography down here, oh, first I want to talk about these molecules. So I have the 3 different molecules in the middle. CCl4 is nonpolar. I know that because all of the chlorines are more electronegative than with carbon, and it creates these polar arrows that all cancel each other. So that's a nonpolar molecule. C's and H's, their electronegativity is so low and so close to each other that we usually say that it's nonpolar. But additionally, C is a 2.5 and H is a 2.1, so they're all pushing inward and they all cancel each other. So once again, nonpolar. The only one that it happens to be polar is this one here, because your chlorine is more electronegative than the carbon, so it creates a pretty good polar bond. And these ones are all pushing inward also. So this one has a partial negative side over here and a partial positive side on the bottom. So the only one that would dissolve in water would be this top one. The other two would not dissolve in water because like dissolves like. Now also when we look about that polarity, that can tell us about chromatography. So let's say we've got our solvent down here and it happens to be water is our solvent. And my paper then has to be a non-polar thing. In order to do chromatography, you have one thing that's polar and one thing that's non-polar. So in this case, I'm making it easy because most of the time we use water as our solvent. And my paper would be nonpolar. Paper is nonpolar. So then if I'm going to decide which molecules are which one, well, this one is the most polar. Water is going up the paper from capillary action, and since water is coming up the paper, it's going to take with it anything that's like it, whatever wants to dissolve in it. So this one being the most polar would be the one that goes closest to the top, since water is going to the top. The next one that would be closer to the top of these two, this one is more massive, so it has a stronger London dispersion forces. With the stronger London dispersion forces, it is more polar, more polarizable would be the word. This one being more polarizable will go further because it'll be more attracted to water than this one, which is a smaller molecule and less polarizable. So here would be my middle, and here would be my end. Now, if I switch this up and make it totally different, like let's say instead of water, I'm going to use something that's nonpolar. Hexane is nonpolar. And that would mean I'd have to have a paper that's really polar. I am not thinking of anything right now, but let's say we do that. If I just switched everything around, then all of these things would be switched around. Since hexane is nonpolar and it's going to the top, it'll take nonpolar things with it right here. So this one would now go to the top and it'll just all reverse. So whatever's going up the paper, polar, will take polar things with it. If it's going up the paper and it's nonpolar, nonpolar will take nonpolar with it. And the last thing we're looking at is distillation. Distillation is this figure in the bottom left. That's the idea of boiling points. So distillation would be, I'm going to boil something over here. Whatever boils most easily will go up, and then the gas will follow down this tube and then drip out the bottom because it's colder over here because there's not any heat over here. So if I look at these three things, the one that will be the easiest to boil will be the one that has the lowest IMFs. The lowest IMF is this middle one, and my highest IMF would be the polar one. Sorry, that handwriting is terrible. And so the higher the IMF, the harder it is to boil because it's attracted to its friends. In order to boil, it has to become a gas and be completely separated from its friends. So therefore, the high boiling point will be my top one here. And my low boiling point will be my low IMF one, which is down here. So if I was to distill these, let's say these three things were inside of this round bottom flask right here, and I was to distill them, the one that would boil first would be this one. Whatever boils first will go down the tube and be caught in this bucket right here. If you heat it a little bit further, you could put a new bucket in, move that bucket over and have it dump into there. The next thing that will boil out is this guy. And then lastly, you could be left with the most polar thing at the end, or you could pump it out the other side too. So that would be the three things about those. And my last one. Okay, and the last one is about taking a look at two different molecules, and if you're given data, and this AP test is going to be all about data. They're going to show you data, and you got to interpret it from there. Explain things, basically. So if I look at this data, I've got different molar masses and their boiling points. And the question says, based on the information in the table about CS2 and CCl4, which one has a higher equilibrium vapor pressure at 25 degrees, and why? So thinking about vapor pressure, let's say I've got a container of both of the liquids. So, and they both have a top over them. And if they both have a top over them, they're going to create a vapor up here, and that's the vapor pressure that they're talking about. So taking a look at CS2, those ones have a boiling point that's 46.5. That's lower than the 76.7. That says to me a low boiling point means lower boiling point means that CS2 has a lower IMF than our CCl4. It'll have a high, in relation to the two of them, a high IMF, because it's really hard for it to separate, so you have to get it really hot. So if this one has a high IMF, that means you're going to have only a few molecules that have actually naturally vaporized at any temperature. And that would mean, in relation to these, a low IMF down here would mean many of them have vaporized. If I happen to have more vaporized, that would create a higher vapor pressure, and that's what's being asked here. Which one has a higher vapor pressure? I would say my answer would be CS2. My reason for that would be a low boiling point means it has a lower intermolecular force of attraction. This lower IMF would result in more molecules coming up in the gas phase. More molecules in the gas phase add to more pressure. If you needed to add about IMFs, I would say between the two CS2 and CCl4, they're all nonpolar, but CS2 would be less polarizable, thus a low IMF, thus all that stuff. CCl4 having a greater molar mass would be more polarizable, which is why I see it has a higher boiling point, because it has a higher intermolecular force of attraction. All right, and last but not least, take a look at our board over here. You can see that we did cross the bridge. The team was able to figure out the riddle. We got a tree here, we got a swamp, and there's a rope. Good thing you guys did have a rope that you found. You didn't find the rope, but you, at the beginning of all of this, you chose 4 different things to bring with you, and rope was one of them. That's a good thing, because you're going to need that today. You need to be able to swing. The assignment for this one is to be able to swing. So you have to have a swing set with a swing. Let's see what team here. We'll decide. Oh, we haven't seen a Mendeleev yet. Mendeleev from 4th hour. 4th hour, you getting picked like crazy. Mendeleev from 4th hour. Your job is somebody from your team has to go to their swing set. You can't go any parks out here because, you know, quarantine. You have to go to your swing set, which has a swing on it of some kind, or a rope of some kind, and swing on it. Show me. It's a beautiful day. At least it is today when I'm doing it on Sunday. And use your swing and show me your swinging skills. If you're thinking, I don't have a swing, well, then check with your other teammates of Mendeleev 4. Do they have any swings they could take a video of? And if you're like, no, then somebody you know, there's a friend of yours that has a swing set with a swing, and they can send you a video of them swinging. If you're like, I don't have any friends with swing sets, okay, then you better be darn creative, because that's all I got. Somehow we have to swing across the marshland. If you land in it, it's like quicksand, and you can't get through it. So that's the plan. Mendeleev 4. We'll see that.